Hello everyone, welcome to Tactica Imperialis and welcome to the second episode of Tactica Tutorialis, my Warhammer Science series. Now, I have seen many requests for different things over the past few weeks since I put out the announce and put out the first episode. And I want to put a little disclaimer of things I'm not going to talk about in the series. Number one is the warp. I'm just not. The warp is not real as far as we understand it. Psychic powers are not real as far as we understand it. So I'm just not going to touch that topic because I don't know where to start and I don't know if there's any science I can even apply to it. The second is getting into super advanced biology, like genetics behind a space marine. I don't think I could do that any justice whatsoever. Genetic resequencing, implants and all that stuff is far beyond anything I could even try to explain, never mind research. So I'm just going to leave that topic alone because I don't think I can do it. But one topic I can do is physics. And the topic I want to talk about today, I know there's going to be people clamoring for the bolt gun, but the bolt gun is nightmare fuel. And I had a look around, and there's some other topics around that I think are also nightmare fuel. But we may get to those later in the series. But for today, I want to talk about one of the newest in terms of how we've seen it, but one of the oldest in terms of how the game sees it, weapons in Warhammer 4. That is the one, the only, the Grav-Gun. Oh yes, we're talking about gravity today. Gravity is a messy old topic, it's a big topic, and getting into the science of this, I expected when I started this series, with this episode's research, to just go, nope, this is rubbish, bop, and just boop it off into next week and be done in 5 minutes. That hasn't quite materialized because I started to think and then my brain started to run and goodness knows where we're going to end up by the end of this episode. So we're going to start off by talking about gravity. So that's going to be part one of this episode. The second part we're going to talk about is trying to rationalize the law behind this thing, trying to explain how it works. I'm probably going to get a whiteboard because I actually bought a whiteboard. Thank you, comments, for telling me to get a whiteboard. I bought a whiteboard, so we'll probably go through that bit on a whiteboard because it's a little bit easier. And then maybe at the end, just for fun, seeing how we do, we'll talk a bit about black holes because, well, we're dealing with gravity. Black holes are always fun. So, without any further ado, let's get started. This is episode 2 of Tactica Tutorialis, and this is the Grav-Gun. So then, part 1 for all of this is dealing with gravity. What is gravity? How does gravity affect us? And how does gravity actually come about? Because that's going to be very important when we get to our Grav-Gun. So, many of you will have heard of how gravity was discovered. An apple fell on Isaac Newton's head and he wanted to know why, and so the story goes that is how he deduced his theory of gravity. Don't know if it's true, wasn't there, it was 400 years ago. But that leads to a misconception that I'm going to demonstrate with my lovely friend here, my Primaris Space Marine. Yes, I bought a Funko Pop, come at me. The common conception is that gravity acts like this. Gravity acts, I'll do that a bit more slowly, straight down. In fact, when we first introduce gravity and the forces caused by gravity, which we know as weight, that is kind of how we teach it. So if I have an object, I'm going to draw it nice and small up here. I have an object, we draw its weight force, because weight is a force, gravity is not a force, don't let anyone tell you otherwise. Weight acts down. That is how we draw gravity for years. That is how we teach you gravity. And that's how I was taught gravity. And even when we were doing full-on, like, complex rotational dynamics, you still do this. You still draw gravity down. And we can also calculate that weight. In fact, I'll give you the equation. Weight equals the mass of your object multiplied by little g. We'll get to little g in a moment. Little g is to do with gravity. It's 9.81 meters per second squared on planet Earth. It varies depending on where you are, and we'll get to why in a minute. But that is a misconception. Gravity doesn't act down, literally, because what even is down? I'm not going to get into philosophy here, but what universally is down? I mean, obviously, it's down, but on the other side of the world, their down is my up because they are the other side of the world to me. We've all seen this paradox before about like falling off the edge of the earth and all that stuff. And this is why gravity sometimes can be a bit of an easy misconception because, well, we get taught it's down, but the world is round, so how does that even work? What even is down? And your brain explodes. Don't worry, we have the answer. Gravity is what we call a radial field. Many of you might have heard of fields, many of you will have heard of gravitational fields. In fact, I'd be amazed if you haven't come across the term gravitational field at some point. And what that means, this other word, radial, means it has to do with circles, or in the case of the Earth and other objects that are actually real, spheres. Things that expand radially, which means that rather than being on a line, you start at a fixed point and it grows out from there in a nice, neat circle as it expands. I'll show you what I mean. If I have my Earth there, then my gravitational field expands in circles as I go outwards. There's my thing. And if you take those to be infinitesimally small, it is like each little slice, each little circle represents a different gravitational field strength. And we know, because of what gravity does to us, that that field makes the forces that it imparts on an object act down. Well, sort of down. Down as far as we perceive it, just stood here on a nice flat bit of planet, but what it actually means is that the force due to gravity acts toward the center of the object that is creating the gravitational field. Or, we'll get to that bit in a moment, it acts towards the center of the field, wherever the center of that field so happens to be. There is an infinitely small point right in the middle here, and the force is acting toward that point. It is pulling stuff inward. That is why the people on the other side of the planet don't fall off, because they're being pulled in the same as we are. That's important, and also means that we get into black hole theory, which we're not going to get into, at least until I get to the end of the video and see how I'm doing. But we can actually measure the strength of this gravitational field. In fact, I've already told you it. It's little g. Little g is defined as the gravitational field strength. That's what it is. It is the strength of the gravitational field. And for us, on the surface of the Earth, at the edge of this little sphere, it's 9.8 meters per second squared, or 9.8 newtons per kilogram, you might say, is the other way of defining it, because we've got a force in newtons and a mass in kilograms, because we're working in physics and therefore we use SI units. Don't worry about it. But can we calculate G anywhere? Yes, we can. And for that, I need to introduce you to a certain individual known as, I think it's Johann Kepler. I forget his first name, but his name was definitely Kepler. Now, Kepler came up with a bunch of laws to do with astronomy. 3 that I think I know of, and some of them are to do with orbitals, but Kepler's third law is the one that I want to bring up to you today. And Kepler's third law states that the force on an object due to a gravitational field, so I'm just going to write a little g, F due to gravity goes as follows. Big G, big M, little m over r squared. So big G is a number. It's called the gravitational constant. It's just a number. Like we had with the speed of light last episode, it's just a number. Don't worry about it. It's tiny. It's like 10 to the minus 11. It's tiny. It's just a number. It's fine. Little m is the mass of our object being acted on. For example, the mass of my little Primaris Space Marine friend here. Big M is the mass of the object that is creating the gravitational field. For example, our planet. And R is the distance from the center of the field that the object is at. So, for example, it could be the distance from the center to the surface of the Earth if it was measuring with me, or the distance to the center of the Earth plus about 4 foot, maybe 5 foot, if you're acting on my Primaris friend up here. And that is the force that we use to calculate that is the calculation we use to calculate the force on an object due to gravity. And this applies to the tiny objects like my Primaris friend, and it applies on the most astronomical scales. This is the forces between planets on each other, and it is this force right here that keeps the Earth where it is, if you like. This combined with centripetal force, or centripetal force if we're going to say it properly, and circular motion is what keeps the Earth where it is. This force pulling us in against our own spinning force, our orbital circular motion force, which isn't really circular, but go with it, is what keeps the Earth orbiting. This is why we have an orbit in the first place, and it's also why we would end up getting sucked into the sun if there weren't more forces in play. Don't worry about it. It's just a really important equation. And the really cool thing about that equation is this is the force on an object due to gravity. And this is the force on an object due to gravity. So what we can say is that these two things are the same thing. We can say that f subscript g equals weight. They're exactly the same thing, and that means we can stick these two equations together. Goodbye go the little m's. So little g is equal, the gravitational field strength at a given point is equal to big G times the mass of the object creating the field divided by the radius squared of wherever we happen to be when we measure the field strength. And that is how we know how strong the Earth's gravity is. Even as we go up into orbit, it's not there is no gravity in space. That's wrong. What's actually true is that the force of gravity is much reduced because the gravitational field strength is much reduced because R has got much bigger. And that is the basics of what you need to know about Newtonian gravity in terms of how we actually feel it and how it works on us. Now I want to take 2 minutes to talk about where gravity actually comes from in terms of full-on cosmological nonsense. And sorry, I'm going to need to bore you for a minute, and that means talking about space-time. Sorry about this, but it is fun and complicated physics, but I think it's nice to know it because it will actually help to explain something in a minute. So, we have established that gravity acts in a radial field and it normally acts around objects that have mass. And we can actually show that using space-time. So, many of you might have seen a little grid representing space-time. So you have a nice little grid and then, one of its bits gets deformed and there's an object sat in it. And then, another bit got a bit deformed and then we have a nice straight line again. We go that way and we go that way and, there's a bit getting deformed there. That is essentially a diagram of space-time with an object in it. This object is probably a star or a planet or some other cosmologically ginormous object. And that is basically bending the carpet that is space-time. And so space-time is like this nice neat grid, and this planet bends it around it because it sits kind of on it, almost like a paperweight. And this is kind of how we visualize space-time and gravity, because this bending of space-time, if I understand it correctly, and I probably don't because I'm not whoever came up with this theory and whoever studied this theory at length, this in essence generates that gravitational field because it pulls objects that are sat around this bent bit of carpet into it like a ginormous sinkhole, if you like. So these objects sat around the edge of this divot, this well. In fact, I'll draw it side on so you get a better idea of what I'm on about. So we have our big object here, and all the little objects that are sort of around here get pulled in to the field. They get pulled in around the object, and we feel that as gravity. So that is where our gravitational field comes from, and it leads to a very important conclusion. Gravity comes from mass. This is going to be really important later. I don't expect you to understand this. If you do, that's great. But I need you to remember this sentence. Gravity comes from mass. If you have mass, You have a gravitational field around you. We don't notice it around us because our mass is tiny and so we don't really see it. But objects have mass and that creates a gravitational field. I need you to remember that. So, now we've introduced the theory of gravity, what it is, how we feel it, where it comes from. Let's talk about the Grav-Gun because honestly, I'm just really intrigued. Alright, so now we've understood what gravity is, or at least I hope we've understood a little bit about what gravity is. Let's talk about the Grav-Gun. I'm going to warn you now, I've done a take of this already, and it gets into some really advanced and really, probably to you very dry, but to me very fascinating particle physics. So you've been warned, this is going to get technical. But if we want to understand what our Grav-Gun is supposed to do, we need to look at what the writers say it's going to do. And what the writers say it's going to do is a stream of particles is fired at a target, changing the local gravitational field around that target. What then happens is this creates a change in pressure, and so the target goes kersplat. So if I put that in very shorthand up on the board, we have particles. They are our ammo, leading to a change in the gravitational field, where G is the gravitational field strength. If you remember, we talked about it in the previous section. That leads to a change in pressure. This Greek triangle, by the way, is Greek capital D, it's delta, and it means change in physics. Leads to a change in pressure, leads to splat. So particles, change gravitational field, change in pressure, crunch, splat, dead. That is how the Grav-Gun, according to the writers, is supposed to work. And surprisingly, this makes the most sense I think you could possibly make of a Grav-Gun. Because up to about there, it works. You change the gravitational field, you change the forces acting on the air because you've got a big little G acting around them, it pulls the particles in and you're under more pressure, and if your armour can't take it, or your internal organs can't take it, you go splat. This bit perfectly makes sense. The problem is that arrow right there. That arrow right there makes it absolutely nightmare fuel for a physicist to try and work out. Trust me, I know. So, how are we going to try and rationalise what in the actual flip is going on? First off, let's recall our equation for little g. Little g is big G multiplied by m divided by the radius squared. We worked that out in the previous section by equating Fg with weight, with Kepler and our weight force. Those two are the same thing, and that gives us the value of our gravitational field strength. So, if we're going to change our gravitational field strength, which we are, that's the entire point, because that's what we're doing with our particles, we need to change one of these three factors. We can't change big G. Big G is a constant. Big G can't go anywhere. By the way, stand over here. We can't do anything with big G, it's a constant, we can't touch it. We can't change R. We're not changing the size of our target. We're not changing the distance at which everything is from our target because we're not shrinking them or anything like that. So that leaves us with one option and one option only. Mass. What our Grav-Gun is trying to do is change the mass of its target using particles. Right. How in the name of terror are we going to do that? Luckily, I think the answer is we aren't, but I came up with a theory that I wasn't really expecting, and I don't think it works, but it was an idea that I had and I wanted to tell you about it. So, if you want a TLDR as to why the Grav-Gun can't work, consider the fact that we're using particles to change the mass of another object by a flipping lot. Because this is a tiny number. This is going to be a tiny number. So if we're going to change this from, oh, I'm just sat here quite comfortably, to I'm flipping squished, we're going to need to change the mass by quite a lot. You can actually probably go and look up the exact sort of strength that the human body can withstand in terms of gravitational forces. And this is also why people who, if we go and live on other planets, could never come back. Because if you went to live on, say, Mars, Mars has a weaker gravitational field, you came back to Earth, you would get crunched by the increase in the gravitational field due to the Earth. In fact, I'm just going to look up now, and I will write it down for you, Mars gravitational field strength, and see if we know it. So Mars's gravity compared to Earth is about 40%. So if G, I'll come back over here now, if G of Mars is approximately 0.4 times the gravity of Earth, it makes sense then that a 40% change in our gravitational field will cause a squish, as an example. So we need to change mass by 40%. Let's just say, for the sake of argument, that to cause a crunch, we need to change our mass by 40%. Which, if you are a, shall we say, 100 kilogram person, which I don't think you are. In fact, let's go with a slightly more reasonable number. Let's say let's use Imperial, and let's say you're 160 pounds. I don't know anyone who is 160 pounds because we don't work in pounds pretty much. But if you're 160 pounds, then in order to be crunched, your mass would need to change by 48 kilos. So you need to gain 48 kilos in mass in order to go splat. Now that's not strictly the correct calculation. I'm approximating because I know that going to Mars and coming back would not be pleasant and would probably kill you. But let's say that for the sake of argument. So how on anything are we going to get 40% more mass into our target using particles? Well, if we want to debunk it, let's say our particles themselves are what are causing this change in the gravitational field. And if we say option 1 is the particles themselves, aka the ammo, can it be due to the ammo? No, it can't. Because if that were the case, you work it backwards, then the gravitational field that these particles create on the target to increase their mass would also work on the bearer and thus kill the bearer outright. Because you can't really diffuse and hide a gravitational field. I don't know if we can create zero-G chambers as bloody ammo holders, but as soon as you fire that particle stream, they're going to be exerting that gravitational force. So as soon as they hit the barrel of the gun, they're probably going to pull the gun and you with them as you go splat. So that's not happening. It ain't the particles. So you want to debunk it? There you go, debunked. Option 2, though, is we do something to the target. And for that, I'm afraid we're going to have to talk about Higgs, and we're going to have to talk about quarks. So, Higgs, you might have heard of Higgs. Higgs boson. Ring a bell? Might do. Quarks, if you did A-level physics, you've probably come across quarks. If you haven't, you probably haven't. Quarks are a subatomic particle that you never find on their own. They change the properties of our subatomic particles. So there are 6 quarks that we know of: up, down, charm, strange, top, and bottom. And they come in pairs: up and down, charm and strange, top and bottom. Up, up, down is the configuration of a proton. Up, down, down is the configuration of a neutron. I could spend an entire 10 days talking about quarks and you'd probably still not get a word of it, so we're not going to. All you need to know is they exist, and the other thing you need to know is that they have very different masses. So for example, the up quark is a certain mass, the down quark has a different mass, and the top and bottom quark are the heaviest quarks of all. The top quark being the absolute heaviest, and to the point that it's so heavy, we've never actually seen one. We've seen the events after the creation of one, but I don't believe we've ever actually detected a top quark. So they're there, and they have mass, and we can flip between what we call quark flavors, and that's where the fun begins. So, if we want to do something with quarks, we need to talk about Higgs. Higgs is the name given to the field that gives stuff mass. That's the thing they tell you on the news. The Higgs boson is what gives stuff mass. And they're about half right. An object moving through a Higgs field, which is a field that permeates all of space and all of time, there is just this thing called a Higgs field. We know it's there. We found the Higgs boson. We know it's there. We proved the theory. And, well, we think we know it's there because science is never dealing in absolutes. So, if you have an object in a Higgs field, they feel a drag, and we feel that drag as mass. So if an object moves through a Higgs field, the drag they feel from that Higgs field is felt by us in the universe as mass. And the relationship between that is that the coupling to a Higgs field is proportional to mass. The more mass an object has, the more strongly it is coupled to the Higgs field, because it feels more drag from the Higgs field, which is why we feel it as having more mass. Okay? Have I lost anybody? I'm asking a rhetorical question. I'm recording this days before you'll see it. In essence, if we give something more mass, then we've changed how it couples to a Higgs field. And that's basically what I wanted to mention. But this brings me back to quarks. I just wanted to mention that because that's how we get to anywhere. If we want to do something with quarks and we want to change the mass of our target, in many ways the simplest thing to do is to just change the quarks. Because if you change the quarks building the target up, well, one, you'll probably kill them because you'll create very unstable particle arrangements that will cause their particles to fall apart and decay into new things. Do it to enough particles, you'll start doing some serious damage. But if you can create enough of a high mass change in quarks, you could theoretically change that mass by a few percent. Maybe not 40, but a few percent, maybe, if you tried hard enough with enough particles. And this is where debunk number 2 comes in. And this is why I'm mercifully going to be able to put that big red X up in a minute. Sorry, spoiler alert. Because if you want to create a top quark, which is what we need top quarks. I will spare you the talk about top quarks because I don't understand them myself in full detail. But the way you create a top quark is through a process known as gluon fusion. That's a Feynman diagram. Shout out Richard Feynman when he created up all of these. And this is how we create top quarks. There's a top quark, there's a top quark, and there's an anti-top quark. So these are what we call gluons. They're linked to a thing called the strong force, and that's what keeps our particles together. It's a force that's repulsive at super short distances, but very attractive at not so super short distances. So it keeps our particles together without stopping. It keeps our atoms together without the neutrons and protons bumping into each other all the time. So these are the coupling constants for the strong force. They are sort of the link that actually transfers the strong force between stuff. And if you get these two things and you fuse them together, they can, for a very short length of time, create some top quarks. A top quark and an anti-top quark. These will then decay or annihilate exceptionally quickly, and you'll get another gluon at the end. This is where the problem comes. Top quarks don't live long at all. They're so massive in the particle sense of the word that they barely last for femtoseconds. I don't even think they last for femtoseconds. As I said earlier, we've never seen an actual top quark in our detector, I don't think. I'm willing to be corrected with what they did with the Tevatron, but I don't think they ever saw a top quark. They saw the aftermath of the creation of a top quark and the jets that prove that there were top quarks there, but I don't think they actually detected, yes, that's a top quark. I don't think. Somebody correct me in the comments if I'm wrong, because I'm probably wrong. But because top quarks don't live long enough, the amount of time they've got where this mass is much increased from the smaller quarks is absolutely minuscule, to the point that the force you'd feel would, you might just feel, you wouldn't be crushed. It wouldn't act fast enough to crush you, I don't think, even if it was at like 100%. Even if that was like loads more, I don't think it would be enough to kill you. And second of all, how do you create these high energy gluons from particles? Because you have to get particles to create these couplings and stuff like that. You've got to get these gluons from somewhere, and that requires really high energy particles, which are probably other quarks. So I just don't know. This was the point where I kind of had to say, you know what? I just don't know. But I'm very willing to say that, as far as I understand it, the quark theory doesn't work either. Yes, we can create these super high mass particles for a very short length of time that can increase the gravitational field strength around the target. But you have to create them in exactly the right place, at exactly the right time, all simultaneously, and expect that to work long enough for it to kill your target. That is either exceptionally difficult to the point that it's basically space science magic, which point fair credit to the dark age of technology humanity, or, in my understanding of it, as far as I think I know it, it's impossible. I don't think the Grav-Gun works. It's really actually quite interesting that it made me think this hard. So I give credit to the writing team for actually coming up with something that made me think this hard and actually think, well, actually, what about? Because I was just going to say, okay, the particles need to be huge, therefore it doesn't work, and just write it off. But when I started thinking about Higgs, and I started thinking about quarks, because I did a bit about Higgs boson in my last degree course, it got me thinking about this and whether we could actually do it. I don't think so, but I'm going to put a little question mark. I think it's impossible. I've done a very bad question mark. I think that the Grav-Gun doesn't work. I'm about 85% that the Grav-Gun doesn't work. Certainly, if you can make it work, you're a better particle physicist than me, in which case, fair enough. But that's my theory. I appreciate that I got into some very, very dry and very, very advanced physics that probably didn't interest 95% of you. But there you go. Now, let's do something a little bit more fun, because we've been talking about this in terms of a particle gun, because that's what the law says it is. But when you think of a Grav-Gun and crushing people, the obvious thing that comes to mind isn't this. It isn't Higgs bosons and quarks and all this nonsense. You start thinking about black holes. So let's talk about black holes for a little bit, shall we? Alright, so we think we've debunked the Grav-Gun using some very, very complicated physics. Credit to the writers for making me think that hard, as I said before. But there's one last topic I wanted to touch on. Something that I think deals very nicely with gravity, but also doesn't really work in the context of things. And we can consider this an addendum on vortex grenades, if you like. Let's talk about black holes. Because I'm sure 95% of you have heard about black holes, but do you actually know what they are, how they work, and their applications for creating something like a vortex grenade, which I know is technically a warp portal sort of thingamabob, but let's assume it's a black hole launcher. Just humour me on this. Let's assume there's a black hole gun. Maybe the Grav-Gun is actually a black hole gun that fires a particle into the target and then creates a miniature black hole that pulls them in and crushes them from the inside. What if? Let's humour it. So, what is a black hole? A black hole is a star. A black hole is a type of star that had a massive, massive amount of mass. It's a really bad sentence. Generally, we say for a black hole, the mass is greater than or approximately equal to 40 times the mass of the sun. That's the symbol for solar mass, by the way. I don't know why it is, it just is. So if the mass of a star is roughly 40 times the sun's mass, when it gets to the end of its life cycle, instead of doing what the sun's going to do and cool off into a white dwarf, shrink down, and eventually just kind of run out of fuel and gently go out, if you like. No. These bigger stars, which have started about 8 times the mass of the sun, boom, up they go, supernova. But with the really heavy stars, the supermassive stars, like this one, they form what's called a black hole. Their gravity from their constituent parts is so great that it all collapses in on itself after the supernova because there's no outward pressure from fusion to keep the thing from collapsing. So in it all goes, and it collapses into what we believe is a singularity. And we're not sure what a singularity is because we've never seen one because of a thing called the event horizon. Here's my event horizon. That's a terribly drawn event horizon, but it has what we call a Schwarzschild radius. And that is this thing, that is the distance. And if you go inside an event horizon, you don't come out. Even if you're a photon and you're light, you don't come out. That's the point of the Schwarzschild radius. It is a point from which no object, not anything, can escape the gravitational force, not even light. The escape velocity to get out of that gravitational field within the Schwarzschild radius is greater than c. You genuinely cannot get out without breaking the laws of physics. Sorry. So what if we had a gun that could create a black hole? Well, let's humour that for a second and say that we have a gun that fires a round of 10 kilograms. And we want to calculate the Schwarzschild radius of that to see how big of a black hole we've got and how much gravity it can actually impart on nearby targets, how much gravitational field strength it has to pull targets in. Well, first we need to calculate the Schwarzschild radius, and we do that using this formula. Schwarzschild radius equals to 2 times the gravitational constant times the mass of the object divided by c squared. We've met g earlier today, we met c in the previous episode, and m is the mass of our object. We've said that's going to be 10 kilos. So that's about 10 to the minus 11. That's 10 to the minus 8 squared. So it's about 10 to the minus 16, though it's about actually 10 to the minus 15 if we're being generous. So let's plug the numbers in. And we have 7 times 10 to the minus 11, 1 times 10 to the minus 15. Also, 1 times the plus 15, so that's 10 to the minus 26, multiplied by 10 kilos, leads to approximately 2 times 10 to the minus 25 meters. For context, we don't have a word for a number that small. That is a picometer squared. The length of a picometer, but squared, is that. It is absolutely astronomically small. Like, ridiculously small. Not even particle physics works on scales that small. Particle physics works on the scale of about 10 to the minus 15 at the lowest. So yeah, it's 10 billion times shorter than that. But what about its gravitational field strength? Now there's some fun we might be able to have. So let's go at a distance of 10 meters. 10 meters seems fair. So we'll go back to our G formula, which, as we saw earlier, is gm over r squared. Plug the numbers in. That's about 10 to the minus 11. That's 10 squared, so that's 100. So we're at 10 to the minus 13. Multiplied by 10 is approximately 7 times 10 to the minus 12 newtons per kilogram. Which, okay, it's a number, but remember what I said about Earth. G for Earth is, actually I'll be a bit more generous, is approximately 10 newtons per kilogram. So our black hole launcher is giving us that much gravity, acting against a force or a field that's 10 to the 13 times stronger. That is 10 trillion times stronger. If you're getting caught by a black hole gun, then you are literally being hit directly in the face by it, and it is only realistically going to be acting on the particles right next to it, and I really don't think it's going to do a lot. So, black hole guns, I'm afraid, are also sadly debunked for the simple reason of you don't have enough of that. There is not enough mass in a conventional human slash alien slash Titan portable device in order to make a black hole gun seem feasible. So that is everything for today. We have talked about the Grav-Gun, we've talked about black holes, we've talked about gravity, we've talked about particle physics, which I don't think any of you were expecting when you clicked on a video about gravity. So I do apologise if that got a little bit technical in some places. I couldn't help it. I started exploring the idea, and credit to the writers for making me think about all of that stuff. So I do hope you enjoyed the video. Let me know what you think in the comments down below. Do my theories make sense? Can you think of any counter arguments that might maybe make the Grav-Gun work using some other theorem that I haven't considered? And just generally let me know your thoughts on this series, on everything in general. I'm always interested to see what you have to say. Next time, I'm not really sure what I'll look into. I'll go back through your comments and see if something grabs me as, oh yes, I think I can explore that. As I mentioned in the introduction, or if I didn't mention it because I'm not sure which take of the intro I'm going to use, the bolt gun and the melter gun are both different forms of nightmare fuel. So I'm not sure if I'll be touching them anytime soon, but it has been interesting, and I know there is one topic I'm definitely going to touch in the not too distant future. For now though, thank you for watching Tactica Imperialis and the second episode of Tactica Tutorialis. See you all again. Bye for now.